Hello and welcome to the second lecture of today's topic on PCB design, and we will talk about PCB design rules. So we learned about PCB materials, the procedure how to make PCBs, and also how to assemble them. And now all that should be wrapped up to a set of design rules one should follow to make a PCB that has all the features able to be easily and reliably produced. And that's the reason of this last lecture. Okay, so PCB design rules. First, just an introductory. That guy is asking, where is the copper? So why is the copper missing here? And the reason is one badly designed the PCB and therefore it wasn't able to be produced perfectly. So yeah, a lot of problems can happen out of the production, and maybe just a small percentage of circuits are not working, but still this can mean quite a big loss in the overall production yield. So yeah, applying the rules to the design by knowing the PCB procedure, manufacturing procedures and assembly and all materials is essential for every engineer that designs printed circuit boards. Okay, so there are several standards that cover this area, and they are divided into two main parts. One is IPC, Institute for Printed Circuits, and JEDEC, the Joint Electron Device Engineering Council. Both these standard groups are issuing their standards that cover the whole procedure in the PCB design and manufacturing process. And there are a lot of things that can go wrong. This is just an example. What can all go wrong in a single wire? And I won't go here into the details, but some of these issues can be mended by improving the manufacturing process. Some of them are issues due to the tolerances, other due to material instabilities, and some of them are caused directly by bad engineering designs. The PCB design flow starts with the schematics and then continues to making the bill of materials, then footprints, routing of the PCB, placing the components, of course, and then preparing everything for manufacturing. And in this process, several people are usually involved. In home environment or in the domestic hobby environment, a single guy is doing all that, but in general, in any company that is involved in this process, several people are working on this project. Some of them are writing or constructing the schematics, the others are placing and routing the PCBs, and then somebody else is preparing for production. Yeah, and I listed a few standards here that are applicable. You are not obligated to know these, but just to show you that they are available, and some of them actually are even bolded or underlined, and these are the most important ones for you, I think. We will use them. The IPC 2221B is the most common, which is generic standard for PCB design. So a few things from this standard, the 2221B. It defines 3 IPC performance classes. What does that mean? Well, you actually can ask yourself, what is the target application of my device I'm developing? And you can either choose it as a general electronic product, which would then fall within the class 1. And maybe it is a dedicated service electronic product, which is actually the device that runs 24/7 as a server or communication devices that are high performance, but the life of people are not dependent directly on them. If you don't count in, let's say, the one that would rather die than have his phone crack or similar. So the class 3 would be the devices that are directly influencing people's lives, like automotive, electronics, health support electronics, flight controls, and stuff like that. So you have to ask yourself what I'm building, and therefore from that on you should choose a set of rules that are actually falling within this category. The next is the producibility level, which divides manufacturers into 3 groups, to level A, B, and C. What does it mean? Well, level A means the most common manufacturer that has limited abilities. Level B can reach higher standards, and level C, the best producers they are. So level A would mean everyone can do it. Level B, some of them can do it, and level C, only the best can do it. So at level C, you will have the smallest tolerances. At level A, you will have the largest tolerance levels. Okay, so now we are going into design rules. So in the Altium design rules, you have some rules that are directly connected with manufacturing rules, such as SMT rules, mask rules, plane rules, manufacturing rules, and placement rules. All these are then directly connected with manufacturing abilities. So you can set them in Altium, and then Altium will automatically follow these rules. That's good, huh? Okay, let's start a little bit with the basic dimensions, what you can do. In IPC standard, you have defined the largest size of different processes in the PCB production. You don't are not needed to know this by heart, but you should be aware that you are limited in size. You cannot make 1 by 1 meter PCB. Yeah. And according to these tooling restrictions, there are restrictions about the edge clearances for copper and components. Can be different, but for tooling to be able to insert the PCB into the machine, you need a certain edge clearance for copper and for components. Of course, you can put your PCB in the panel. So your PCB can be a part of the panel, as you see here. So at the end, well, you can say my PCB will be panelized, and all the tooling and manufacturing edge clearance is done by the outer frame of that panel. So there are some rules how to make the panels. We will not follow these because usually the panels are made by the manufacturer. So what you do, you design the PCB, and all the paneling is done by the manufacturer. And the PCBs are then cut out of the panels on different ways. Either you make the grooves, or the manufacturer makes the grooves and makes small holes here when the common bridge is. These are called mouse bits. And you have to follow some rules again that are telling you how far from the edge you can go with the copper and with the components as well. Because being very close to this edge means that the manufacturer has to follow more strict tolerances, and that means that the PCB would be expensive. These are just guidelines that are not how to say absolute values, but all that numbers, all that distances, if they are followed, you're on the safe side. But for each PCB, you should contact the manufacturer you are intending to send your designs to, and they will tell you what they can do. This is an example of this so-called tab routing. The mouse bits are here, and these are the grooves or the routing areas, and here you can just crack your PCB off the panel when it's finished. So this is one option, and this cracking of the PCB would leave us a part like that, a leftover, and if you crack it, or at the cracking point, you can peel off some of the solder mask and leave the copper exposed, which you don't want to do. So that's one of the reasons why you should move your copper away from these parts for a certain amount. You can also use rescoring. A rescoring is actually just milling your PCB with a mill in a triangular shape, and here the PCB is weakened, and you can cut it, or you can break it off. At least, again, here the solder mask is exposed, and when you cut it, you can also damage the solder mask. So I just took one value from one manufacturer, that your trace should be at least 0.2 millimeters away from the edges, but that I would say it's quite close. And the reason why you would go so close, of course, is when you make really small PCBs and you don't have any space. And here, if everything goes smoothly, you still have a problem of your edge. The edge is rough, and it's exposed to all the mechanical issues, like the solder mask, which is here, and this is the track, can get damaged, and therefore your track should be kept away from the edge, so that the solder mask has some extra free space until the track is. So, as I said, these values of that dimension change a lot from manufacturer to manufacturer, and it depends on the class of your device, whether you want to do a general, less reliable electronics or more reliable electronics. This would change. So this value here, 0.25 millimeter, is the ability of the manufacturer, how low it can go. Okay, fiducial. What is a fiducial? A fiducial is a mark that pick and place machine and other machines, also manufacturing machines, are using to orient themselves. So it has a certain shape, and the most common is the donut shape. And the donut shape is shown here. It needs a certain clearance around it. So this is a pad, which is metallized, or it has a surface finish. And then there is a solder mask around, and this is the gap in the solder mask. And these are the minimum and the preferred dimensions according to the IPC standard. And the fiducial looks like that. So you see the surface finished pad and the solder mask opening here. And this is where it has quite a high contrast, and this is how the machine can see it. And how many of these fiducials should you put? Well, at least 3 global fiducials are necessary, and these 3 global fiducials are used to orient the whole PCB for the machine to get the correct coordinate system. So it needs to orient the PCB and also check for the height. So that's why you need 3 points in a 3-dimensional space. But there are other fiducials which can be also applied, and these are called local fiducials, and they're meant for fine adjustment of your optical coordinate system optically around fine pitch devices, where maybe a tolerance of some error can be built up when you are moving very far away from original fiducials. So we have global fiducials and we have local fiducials. PCB masks. Well, several things can happen with this solder mask problems. Thing is that solder mask is not aligned inherently with copper. You see that solder mask is misaligned here. So the solder mask should have some so-called swell. Does it mean? The opening in the solder mask should be larger than the size of the pad. So if the solder mask is not aligned, it would still sort of fit on the PCB. And this is acceptable misalignment here, just at the edge. Usually this solder mask swell is in range of 0.1 to 0.2 millimeters, depends on the manufacturer again. Here you see the protection of the solder mask that protects the narrow protection of solder mask across the track, and here is wider. Now thing is that if the solder mask is very narrow, then it might easily be peeled off mechanically or during the normal operation of the PCB. So very narrow solder masks are not allowed. So the solder mask should be wide enough or it shouldn't be there at all. This is how the mask alignment check feature looks like. You see, this is copper. This is silk screen printing, the top overlay for any values, numbers and stuff. And this is opening the solder mask. And this is how you can check alignment of the solder mask during the manufacturing and other masks as well. And yeah, the first rule, as I said, is solder mask sliver and expansion. What are these two? As I said before, solder mask expansion, or in some software it is also called solder mask swell. It is this increase of the opening regarding the pads so that the solder mask can be a little bit misaligned but still okay. The other is so-called solder mask sliver. The solder mask sliver is actually the minimum width of the solder mask that still guarantees mechanical stability, and this is in the range of 10 mils, which means 0.25 millimeters. So if the solder mask is narrower than that, it might already peel off. Again, it depends on the manufacturer. And these are some manufacturer data, what you can do normally or if you pay more. Paste mask. Paste mask is another mask that we should set the properties to, and this is the rule that I show here is paste mask expansion. So the paste mask actually is a stencil that is used to print the solder paste. And I already mentioned in the previous lecture that the paste mask should be decreased a little bit. So the opening should be decreased with respect to the pads, and this then assures that the paste does not spread around too much. And this expansion here should be negative, so put -2 mils. This is, I think, changed in some of the Altium designer softwares, some of the versions. So now in the latest version you should put -2 mils here in order to be to make the contraction, not the expansion. This is how the solder mask misalignment looks like. See, at the edge. And this is solder mask sliver. Very narrow area, and it can be easily peeled off. And if it goes over the copper area, this copper is now exposed and it would corrode. So in this case, you would have to get rid of this part. So the whole track is covered with, let's say, solder or gold or whatever you use for surface finish. What about holes? We have two types of holes. According to standard, the first type is called unsupported, and the second are supported. What's the difference? Unsupported holes are those who are not plated and are passing through. So holes that are through holes and not plated. They are using for tooling or mounting different mechanical features on the PCB like heat sinks and similar. Supported holes, which are plated, which have copper plating, are divided into three or even more subgroups. Blind, these, buried, blind are these, number one, buried, number two, and plated through holes, number three. And the blind wires are also micro wires, can be micro wires, and some of the plated through hole wires are also intended for thermal conduction, so they are called thermal wires. So you can increase the thermal conductivity vertically through the PCB by applying thermal through-hole wires. Okay, what about hole diameters? Well, there are some tolerances of spindles of the tools, and these are typically 25 microns. And the problem of drilling holes actually is the tool itself. So you cannot have very long and very narrow tool. And you can imagine having a very long and narrow tool would mean that this spindle would, or this tool would just break. So the tool has its limit regarding the, if that's the, it has its limit, and the width and the length or the ratio between length and the width is limited. So L over W cannot be arbitrarily high number. So this ratio is maximum 10, maybe 12, recommended 5. Recommended means that you will have no problem with these holes. So the ratio between length and the width of the holes is limited. And here is the chart which shows for different classes of PCBs what is the minimum width of the, or minimum diameter of the plated through hole wire. And let's say for normal electronics, and I'm sorry, this is for buried wires and this is for blind wires, but this is for normal wires. So for example, if you go to 1.6 millimeter classical PCB, minimum diameter, it would be in this range, recommended 0.3. Next is the ring around the plated through hole, because the ring has to have a certain width, and that width is divided into 3 parameters. Of course, the hole diameter, and then the minimum width of this annular ring, and the fabrication allowance. A fabrication allowance is the tolerance of this hole. So that, okay, the tolerance of the hole would tell you how much you can miss the center of this ring. And the tolerance of the hole in the level A manufacturing level, when you have the worst or the general manufacturers, it's 0.4 millimeters. Then it go up to 2.2 at the best. So if we want to calculate it, it's not that hard. Let's go for a 0.3 millimeter hole, diameter of 0.3, so A is 0.3. The B, if you go for normal general electronics, external supported holes, it's 50 microns, so 2 times B is 0.1 millimeter. Okay, and the C, fabrication allowance, let's go for the worst, so 0.4. That would give you altogether 0.8. So the via 0.8 0.3 would be the one which you would make without any problems. Of course, you can choose a better manufacturer, maybe level B, and then you would go to 0.65, 0.3. That would be a better wire in that sense. A smaller wire, but usually now, I would say a large portion of manufacturers can produce a level B tolerance. So that's how the big hole looks like, big wire with a small inner ring, but still all according to the specs. See here how the hole missed the center for almost the whole diameter. And thanks to the annular ring, big annular ring, we could make it. And here you see the peeling of the solder mask. That happened, I don't know why. You see the hole tolerance at minimum. I don't know if this is 50 microns, it seems less. And we had some problems with that. We had a PCB that we sent to producer, which had, and it's taken from, this is the picture from that PCB. These holes, some of these were not conductive anymore. You can increase the probability that this would go through by adding teardrops. A teardrop is actually a feature in Altium in which you can add some smooth transitions from the pad to the line. And by that, you can actually increase the probability that this wire is going to be okay. Let's say if the hole is drilled here, then you may get a problem with conduction, but if the teardrop is made, then it might just go through. And this is how the teardrops look like. Nevertheless, this hole was drilled totally off the center, so it didn't help. This wire was not conductive, even though the teardrops were used. So again, these are some data from manufacturers, what it can do. So aspect ratio 10, advanced even 12. That's the diameter of the hole and height of the hole, and all the other dimensions are shown here. So yeah, you should check your manufacturer before you start defining design rules in your PCB, and then before you actually make it. These are rules for plated through holes, and these are rules for blind and buried wires. Okay, let's talk about thermal relief. A thermal relief is actually a way how to connect the wire to the copper plane. The problem of the wire, if it is connected to a big copper plane, is that it dissipates heat quite well. And dissipating heat in this case of soldering is not a good thing. In soldering, you have to heat up the part where you will solder very quickly. And if you have a big copper plane, this would slow down this process. And therefore, you have to use so-called thermal reliefs. These are these fingers that connect this hole, plated through hole, to a copper plane. You can use 4, 2, or similar. And it's important for soldering. And if this is used, then this pad would heat up quickly and it would solder easily. This is how the thermal reliefs look like in practice. Now, what about SMT pads? The SMT pads also have to use thermal reliefs. And still, look at this image here. This pad is connected with a single line, and this pad is connected with 3 lines. And here is a wire. Okay, let's check out what can happen. This can happen. If both sides of your, if you have a very small component like a capacitor or resistor, and both sides have different, each side has different thermal conductivity or thermal capacity. That means that one side would heat up quicker than the other. And if that happens, then one side would act with the pulling force of the solder before the other side. And this would then move the component in the wrong direction, in the direction you don't want. You can also get so-called tombstone component, the component that stands vertically because of the melting on one side before the other. Or you can just move the component or lift it a little bit. All that can happen. And how you can get rid of these problems? Well, you have to assure that your component will have the same thermal properties on both sides. Here, if the component is large enough, let's say 0.8, 0.5, I don't see a problem. But if it's smaller, 0.6, 0.3 or 0.4, 0.2 or even less, then you should be more careful about it because it's so light, any force difference can move it into any direction. So you should make sure that both sides have the same number and width of wires, like here. This is not a good idea. This would melt first and this would melt also first, and here the melting will take longer. And as long as you keep the small part or the connecting part to the pads the same, you're on the right side. Also, this I don't think is that bad. The only, I would say, wrong, poor design is here. If you want larger current, well, you can go with several narrower traces. If you want to use wires and there is a problem, then move them away. If you want to put wire really close to the pad, which in case of, let's say, bypass capacitors, you will learn later, it's quite necessary, then it should be covered with solder mask. But then you should do it the same on both sides. So this is certainly not acceptable, putting wire on the pad or putting wire next to the pad but not keeping both sides of the same thermal conductivity, of same thermal properties. So you should maybe use thermal reliefs, and if you put a wire very close, you should cover it with solder mask, because here, even though the wire is separated from the pad, the solder paste would be sucked into it during the soldering process. So you should cover it. So now you have a pad that is isolated with the top solder mask, and it is connected to the copper plane with thermal reliefs. And this would assure you that your soldering would go smoothly through. The wire tenting looks like that. Wire tenting or covering with solder mask is a technique where you fill the wire completely, and it's not even, it could be filled, this is called mask plugged, that it's completely filled or just covered. But if the wire is covered, it should be covered on both sides. Covering wire on one single side, it's not acceptable. Well, it might not provide a big problem, but if it does, what will happen? Some gases would stay inside and it will start to corrode aggressively. These gases or liquids from the manufacturing will not get out because it is opened only on one side. So I recommend using tented wires, but if they are tented, they should be tented on both sides. Filling wires with solder mask has another advantage if you decide to do that. you can make so-called via in a pad. If you have a very high density FPGAs, let's say, and in BGA format, then you have to get from the middle pads towards the outside of the component by using vias, because you cannot go on the same side. But these vias take a lot of space, so you can make a via in the pad. But in order to do that, you don't want a hole in your pad, because that would suck the ball inside. So you need a so-called via in a pad where the via is totally filled. Here is the covered area with copper, and then you have a surface finish, which in case of BGAs is usually gold inning. So yeah, that's an option, but it's an expensive one. All right, let's go to the wave soldering problems. In wave soldering, there are some things you should be even more careful about. Wave soldering. Okay. What can happen in wave soldering? Well, solder bridges can happen, so that several pins, or at least two, are shorted together. And the solder bumps can happen. That's a problem because you don't know what's going on inside. You don't know whether the pin is well soldered or it has a void. And the copper can be lifted off. If this happens mostly on a single-sided PCB where holes are not metallized, they are not supported, and they can easily be peeled off. So at single-sided PCBs, you should use thicker copper layers and larger pads so that more area is attached to the PCB. Or some of the pads of your components are not soldered. This can happen because of different reasons, but the reason which you can influence the designing reason is shadowing. I will go through these problems and rules very soon. Okay, first design rule, which is the most important one, I would say, among all regarding wave soldering, is the orientation of the components. So what happens during the soldering process? When the PCB is taken across the solder wave travels in this direction. So when it comes to the pins, a big bump of solder gets stuck on the pin, and then when it moves, it starts to jump from pin to pin. And when it comes to here, it jumps to the next component, and then to next component, and then to this one, and so on and so on and so on. And when it comes to the end, it has nowhere to go. You have to provide a space for this solder bump to finish its journey. Now, if the components are oriented like that, there are a lot of ways for this solder bump to jump from pin to pin, right? There are no, big gaps in between. But here, you can get some problems if the components are oriented perpendicularly to the solder wave traveling. Then you see here, if this distance is too large, then this solder does not have an option to jump over, so it will just get stuck here, and you will get several shorts. So orientation of the soldering of the waves according to your components is essential. So you should know at the beginning already how your PCB will be placed in the machine, and according to that you should place the components to orient them according to the solder travel. And the size of these components, the pitch of the pins, should not be below 0.5 millimeters. 0.5 millimeters is at the edge. So you should maybe go less, let's say 1 millimeter or 1.27, which is 50 mils. So below 0.5, don't go, because it will not be able to make. And the direction, yeah, usually the PCB is put in the machine along the long side. So don't use any connectors at the long side, because these connectors would stay in way. Because the fixture, the tooling fixture, the conveyor fingers will have to be holding the PCB at the long edges. So put connectors on the shorter side of the PCB and take care of the correct orientation of components so that the solder is able to jump from pin to pin. So maybe I can make it even more picturesque. Okay, jumping here, pock, 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 hop, pock, 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 hop, 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 and so on. So maybe here it will have a problem. Tsunk, tsunk, oop. Or maybe here, check, check, where should I go? Okay, I will make a big bump here. And so on. Maybe here also will be a problem. And here you may get a problem with the solder shorts. Okay, the last pins here are always the problem. These, you will always have issues with these, because the big solder bumps at the end are always present. I will show you how to get rid of it. The other problem is the component shadowing. If you put a big component at the beginning of the direction of the solder travel, you will make a shadow to these smaller components. So you should put the smaller components first and then the bigger ones. This is an example of shadowing. This big chip casted a shadow on this capacitor here. So you see here there is too little of the solder. Okay. So if you want to get rid of the shadow, you should put components far apart, far enough apart, but yeah, this, for example, this component can still cast a shadow to that pin here. If they are too far apart, you will have a problem with the solder bumps. If they are too close, you will have a problem with shadowing. For example, this is a through hole connector which has some SMT components on each side, and the direction of wave is such that these components do not present a shadowing issue. But here, these components do present a shadowing issue, and you should take care that the smallest are close to that connector, let's say. So this is schematics of the shadow that these components are representing for a wave. Before I told you about the problem of solder bumps, how to solve them, well, you should put so-called thieving pads, solder stealing if you want. So what's the thing here? According to the direction of the PCB flow, you should put some areas, exposed metallized areas, on which the solder will, the leftover of this solder bump would stay. So here at the end, if the direction is upwards here, these are the thieving pads for this big connector here. Here as well. Well, you can, there are some certain rules again how to put these pads, what are the minimum or maximum distances, but maybe take care, of course, first these pads should be there, right? But if you're putting the pads, don't connect them. Put the pads unconnected. Because if this pad, let's say here, accidentally makes a short to that one or that one, then you will have a problem. If it is unconnected, it can make a short to anywhere. Maybe here it's not an issue because this resistor is very far away from that pad. But if it was closer, then you could have a short between these two pins, and that would cause problems. How about TQFP cases, like here. You see it also, the integrated circuits that have pads on all four sides can be soldered in wave soldering, but they have to be aligned at 45 degrees, oriented at 45 degrees. Why is that? Because now the soldering bumps can jump from pad to pad quite easily. Well, here they can't. Here they can. Here also. Here they can't. So by putting them at 45 degrees, you can put two teething pads at the end and you are more or less on the safe side. This is another example of so-called drainage pads or teething pads or whatever you call them. So there are several names for that. Again, soldering wave direction goes here down, here as well down. So these are areas where the excess of the tin of the solder would stay. Again, maybe you will have a problem with shorts here. So if not absolutely necessary, don't put these components too close to this soldering teething pads. Here are some rules which you can obey about the distances between different types of the cases. What about wires? Under the component, you can have only tracks, not wires. Wires are just too risky to have because they can suck in the solder and you can't see it because it will be under the component. Even though the component is on top layer, the solder can be sucked through the wires from bottom side and it can make a short on top layer without even noticing it. What about the copper line width? This is a totally different now set of rules. And yeah, it's connected with the current that is the line is carrying. And of course, each line has some ohmic resistance. And you can calculate the resistance of such a wire using copper conductiveness and the thickness of the copper. So for a typical copper line on PCB with the depth of copper 35 microns and 0.3 millimeters wide, you get 17 milliohms per centimeter. Well, is that a lot? Well, it depends. Let's go into the standard. These standards will tell us what is the required cross-section for a certain current that due to resistive losses, the line would not heat too much. So this equation tells you about the over temperature with respect to the ambient temperature of the line, the cross-section of copper, and some factor which is different whether we are talking about outer or inner layers. So this is a graph in which you can get the current according to the cross-section and the over temperature we are looking at. The inner layer lines cannot dissipate heat so efficiently as the outer layer lines, therefore this factor is lower. But it's quite hard to work with square mills, and so I rather go into the online calculators. So let's show you the calculator which is used for that. So this is the calculator. It's called Saturn PCB Toolkit. I'm not sure if I've shown you it already, but it's very useful. You can download it for free. And the conductor properties, you can type in what you want to solve, whether you want to solve for the conductor width or for current. Let's go for conductor width. I want, let's say, 5 amps. The length of the line is maybe 10 centimeters. It is a DC current. And then we can say we have standard FR4. I only want 10 degrees higher temperature than the environment. Environment is 25. It is an external layer. And the thickness of the copper is base 18 plus 18 of the plating. So together 30 36, 35 microns. Let's solve it. So this is the DC resistance is 7 milliohms, cross section in square millimeters, the width is 7 millimeters. So the external line should be 7 millimeters wide. Well, maybe we can go for thicker copper. 18 plus 53 is 70 altogether. And with double the thickness of copper, we get to 3.6 millimeters. Okay, we can allow for higher temperature rise. Maybe we can go to 20 degrees. Then we are at 2.4 millimeters. So that's it. Very, very straightforward. And you get the result. So I did calculate a little bit using this calculator, and I show you a few results. And yeah, for outer layers at 10 amps, at 10 degrees difference, we get to 7.6 millimeters wide line. Quite a lot. Now the problem is the copper thickness. These are two charts that tell you what is the tolerance of the copper thickness. If you say I have 1 ounce per square foot, that means nominally 35 microns, it could be between 30 and 50 or 55 even. So the whole, I would say, procedure here shown here, you start with the base copper, then you do the plating according to the class. Class 3 is more plating, the class 1 or 2. Then there is some tolerances. This is called process allowance. And then you finish with the copper between 47 and 52 microns. Now, this is the starting point for outer layers. What about inner layers? Or for inner layers, you start with 1 micro, let's say 1 oz, and you finish with down to 25 microns only. This is just to tell you that copper thickness is not a fixed value. It can be very different from case to case, from manufacturer to manufacturer, and according to the class of your device, what you're working on. And clearances. Let's go talk about a little bit about clearances. And the clearance between the distance between different parts of your PCB, different conductive parts, is defined by the maximum voltage that is applied between these two parts. You can set the clearance in Altium in this array, in this matrix, between different features. And electrical clearance, as I shown you, I told you that it's defined by the voltage level between two pins, but are two parts of the device or of the PCB. But at the end, of course, it's also limited by the manufacturer abilities. So you would maybe want to make clearance of 0.5 millimeters or 50 microns, but nobody will be able to make it. So, electrically speaking, that clearance depends on the voltage, of course, but also of the type of the conductors. For internal conductors, so lines within the stack, inside layers, the surrounding is FR4, epoxy and glass fiber, and the breakdown voltage of that is quite high. So the distances are really, really low. So even if you're talking about 500 volts, it's still a quarter of millimeter. If we are talking about external conductors, it's a difference whether they are coated or uncoated. If they are coated, then it's a little bit larger distance required than for internal, but not significantly. But if we're talking about uncoated lines, uncoated tracks, then it depends whether we are below 3000 meters or above 3000 meters. So what's the reason here? The reason is that is here. The electric strength of the air, it's very, very dependent on the atmospheric pressure. So when the pressure goes up, the electric strength goes up. If the pressure goes down from here, the electric strength go down. Until the pressure is very low, it will go up again. If the pressure is zero, it is infinite, right? In vacuum. So there is a minimum, and we are here, and then we go down. So the thing is, you should take care if your PCB has uncoated external conductors. At a certain height, the pressure is lower and the distance should be larger because the electric strength of the air is lower. And the difference is really, really large. If you're talking about 300 volts, it is 10-fold. That's a lot. Now, what do we mean about uncoated? Aren't all PCB actually coated? Well, not exactly. PCBs are, of course, usually coated, right? Let's say this one. Yeah, I have it here. It's coated, it's green, right? But not exactly. All these shiny opened parts of this PCB are actually exposed. They are uncoated. So this PCB is treated as uncoated. So where is the problem of the distance between the tracks? Usually it's a problem next to the chip. And the integrated circuits here you see all have very dense leads, very small pitch. And therefore these pins are uncoated and they are very close. So they fall into the category of external uncoated pins. So this PCB shouldn't be used about 3000 meters, for example, in this design. Okay, why 3000 meters? Well, because that's quite easy then to distinguish between the electronics that goes into space and avionics and electronics which works on Earth. About 3000 meters, not a lot of people live with electronics. If you're a climber, you may think of getting a better phone that has a coated polymer coating, let's say. What is that coating? It's an extra coating you put on top of assembled PCB. So you spray it with some coating that actually covers all the conductive parts of your components, tracks and everything. And that's then the polymer permanent coating. Okay, these are restrictions from manufacturer about the width and the spacing between the lines, and it has nothing to do with the voltages and currents. It does with the manufacturer's abilities. At the end, you should also know about the mechanical problems that can occur if you have a mechanical fasteners, screws and so on. These are all mechanically affecting the PCB, and you should be away with tracks and everything from these parts as far as you can. At the end, I would like to finish with a few slides showing the design, how a nice looking design, about nice looking designs that are not just nice looking from point of not just nice looking, but they're also, because of the order, easily readable, and you can also easily find any mistakes. I mean, here you see that it's good to have sort of order in the component placement. that all components, if possible, are oriented in the same way. If they cannot be oriented the same way, they might be just grouped together, not just thrown on the PCB like you would throw a bunch of, I don't know what, corn. So why is that? Because by that you can just look at the PCB and you already see an error. If one of these diodes was turned around, you would immediately see it. If one of these was turned around, you wouldn't. What about the silkscreen or overlay rules? Well, these rules say that it's nice to have all text oriented in the same direction. If that's not possible, then maybe use two directions, two preferable directions, and don't mix them. Every text should be next to its corresponding component. The text should not go over the holes, because if it does, then you don't see it. It will not be visible. It should not go over the pads, because then you would have problems soldering. Of course, the manufacturer detects these errors and corrects, so usually this text will not be visible. Don't put text under the component because you will not be able to see it. If components are too close to each other, then put an extra text just in the vicinity and mark it accordingly so that you are quite sure which component is which. You see here a problem of text over holes where the manufacturer actually corrected your design before it put into the production by removing the part of the text which would go over the plated holes. So here it's a little bit harder to read it then. But you cannot rely yourself on the manufacturer ability to correct for your errors, and therefore it's better to do it already in the design phase. So by that I would like to finish this lecture about design rules. After this lecture you will be able to do all that stuff. So you should know a few numbers, just a few, not all the numbers I've shown today. I've shown a lot of numbers, just a few numbers. So I would say minimum lines and spaces between the lines. So the minimum clearances. That's good to know from manufacturing perspective. And let's repeat it a little bit. So I would say minimum width for manufacturer is 0.1 millimeter and the clearance also 0.1 millimeter. In this range. If you want to be on the safe side, so this is the width and the clearance between the lines. So these are two lines, one line and the second. So width and the clearance. To be on the safe side, maybe it's better to go to 0.2 and 0.2. This is what everybody can do. And then hole sizes. The ratio between the height and the width of the hole should be in the range of 5. If you want to go to the edge, go to 10, but 5 is preferable. What else? Annular rings. You should know the formula for annular ring. So the width of the hole, the diameter plus 2 times the annular ring, I think it's A or something, or this is A and this is B, right? Annular ring plus C, the allowance of the tolerance of the hole drilling process. So these are mainly the numbers you should remember. 2.2.2 for clearance and for width minimum, L over W, and the typical hole width and the annular ring width for the wire is, let's say, in a range of 0.6, 0.3 millimeters. Yeah, 0.65 if I'm more on the safe side, let's say, for those who want to be more precise. So 0.65 is the diameter of the wire and 0.3 is the hole width. Okay, just to make sure that you understand which numbers you should remember. And you should be able to set all these design rules in Altium Designer. That's what we will learn during the laboratory course. You should be also able to follow the rules so that you can design the PCB following these rules. And these rules are good to be, so you should know what are the basic rules for placing the components for to designing the whole PCB with respect to the manufacturing process you will choose, namely the reflow soldering and the wave soldering, and what you should do and what you shouldn't do. All that we talked about. About the numbers, that's all you want to know, which are listed here on this white top right area. Literature. Some of the standards, you can download it from this spooky Russian site if you want. There are some other documents which I checked and got these all information from. So that's about it. So have a nice afternoon, and I hope that I was not too long today. See you.